All right, so we're going to go over 4.1's takeaways. So this is what you're supposed to like take away from the lesson. So it says features of f of x being 1 over x. So let's like just graph that little thing just so that we have this picture in our head, right? So the interval from 1 to infinity, from 1 to infinity, what is happening? Where is it going? Where is the function going towards? Yeah, it's going towards 0. So here I'm just going to write let's do this in math language so that you guys all see this. So as x goes towards infinity, f of x goes towards 0, right? And that makes sense because, right? That makes sense because like it's just going down. Mathematically speaking, can you tell me why it would go towards 0? Like as the numbers get bigger, what happens to your share? That's what we were talking about yesterday. Yeah, as you divide by larger numbers, your share becomes less and less, right? So as long as you're understanding this thought here, you're pretty good. I'll change colors so that at least it'll stand out for the next line. But what happens from 0 to 1? What happens from between here and here? From here to here? What happens? So here, I want to say the same thing, right? So here, but I'm going to go towards 0. As x goes towards 0, as x goes towards 0. So we're not going this way. We're not going from, like, I don't like this. I like saying it like this because you don't know, are you going from right to left or left to right? Right? So I'm going from right to left. As I go from right to left, where is my arrow going? Where is it going? Towards where? What number is that? Nope. As I go towards it, where is my number go? Yeah, infinity. So this number is infinity, right? So as x goes towards 0, as it approaches 0, my number, my y is going up towards infinity. And I can grab this thing, right? And I can drag it all the way and I can zoom out. It's still going towards infinity. Will it ever equal to 0? Will it ever, well, can I ever plug 0 in? Everyone says, no, Ms. Johnson, because we can't divide by 0. We had a long conversation about that, right? The conversation was something like, if you won the lottery, how many shares does each person get if 0 people are sharing it? And that doesn't make sense because if 0 people are sharing it or dividing it, no one gets, and then so some people were like, but it's 0, Miss Johnson, but that doesn't even make sense because 0 means that there was nothing to share. I'm telling you, there's one share, like there's one lottery winnings to win or to share, right? So that doesn't make sense. Okay. Yes. Then nobody, yeah. The other way that we were talking about it yesterday in, not yesterday, but in advisory, we said, if you say that 1 divided by x equals to 0, right? Right. So if you think this is a question mark. So can you remind yourself, like, if I say 10 divided by 2, you guys would all say, oh, Ms. Johnson, that's 5. And I'm like, okay, well, prove it. And you would say something like, oh, because 5 times 2 is 10, right? And I'm like, yeah, that's right. So if you're saying this is true, then you're also saying, so 5 times 2 equals 10, then you're also saying that 0 times x equals 1. And what have you known since you were like in 3rd grade? What was your favorite multiplication table? Everyone says zeros. Why was 0 your favorite multiplication table? Yeah, because 0 times anything is gonna be 0. But then this conflicts with what you just wrote, right? You said that if 1 divided by x is 0, then it's also true. This is called fact families, right? When you were little, like if 10 divided by 2 is 5, then you also know that 5 times 2 is 10, and 2 times 5 is 10, and 10 divided by 5 is 2. Do you guys remember fact families? That was the family of facts that were all linked together. So his fact family says, if you say that 1 divided by x is 0, you also think that 0 times x is 1. And even a third grader would come up here and tell you, no, right? They'd be like, no, because anything times 0 is always 0. So because this is false, let me cross this out like with some like red something. Because this is false, it implies this is false. Okay, so get that in your head. I know students always, you're not the only student who thinks that 1 divided by 0 should be 0. You're not the only one. It's a classic mistake. So if you keep thinking about this, it'll make more and more sense. Okay. It's not just something that mathematicians have decided. It actually makes sense. Okay. So here, this actually makes sense. So here, if you divide, so here it's as you divide by a larger number, we're not dividing by larger numbers. From here, I'll go back home. Here, we're dividing by really what numbers? Really, really small numbers. So, I wanted this to be orange. Make this orange. Can I do that? Can I go like this? Hey, make yourself orange. Yeah, good. Sorry. So now I want to type this in orange. Okay. So here, as you divide by smaller numbers, what happens to your share? So as I divide by like half, yeah, it gets larger and larger and bigger. Your share gets larger, right? So classic example is pizza, right? So classic example is going to be like this, something like you have a pizza, you're splitting it with your best buddy, and then someone else walks in and you're like, oh shoot, got to share it with them too. So now your pizza is getting smaller, and then more people come. So if you reverse that, the less people you have to divide by, the bigger your share gets, right? And then that's pretty good. Okay, so what about this? What are characteristics? What are some characters? What's interesting about this? What did you guys say about this? You guys said, remember when we started doing the negatives, what word did you use? You said something and I was like, oh, you understand this part. Yeah, it reflects. So it's a reflection of itself. So let me see, let me go different color. So we can say something like this. Where is my little guy? Are you going to type? Yeah. So we could say something like its inverse is itself. And you're like, what, Miss Johnson? Is that true? Yeah, it's true. So if I go like this, do you remember inverses? Do you remember how do I get rid of you people? Okay, I can't get rid of you. Oh, I can get rid of you. Just kidding. So if I take an inverse 1 over x equals to y, do you guys remember this? We switch x and y, so we get x, sorry, this is hard typing with a mouse. Okay, and then if you wanted to solve for y, you would multiply by y, right? So you would get yx equals 1. And if you want to get rid of that, then you divide by x, right? So you get y equals 1 over x. And you're like, Miss Johnson, we're back to the beginning. Yeah, he's a reflection of himself. So therefore, he's an inverse of itself. Does that make sense? So this is a classic question. Find the inverse of 1 over x. And you're like, Miss Johnson, you can't trick us. It's 1 over x. Got it? The other thing that I wanted to share as well is that it's an odd function. And we've kind of talked about this. It's an odd function. And when I say it's an odd function, this is what I mean. F of x equals negative f of negative x. Oh, I should have done this as a thing. Why are you, there it goes. I'll just leave it. So what does that mean, Ms. Johnson? It means if I go to the right to 5 and I get 1/5, I plugged in 5, I got 1/5. Now I'm going to plug in -5, I get -1/5. Do you see how they're opposites? They're opposites. This is called an odd function. An even function we said was like x squared, right? And the reason why it's considered an even function is because if I go to the right 2, I get 4. And if I go to the left 2, meaning -2, I get 4. So the positive and the negative of the same number gives you the same value. They're even Steven. Does that make sense? Even meaning the same. Odd meaning opposite. All right, talk about symmetry. What does symmetry mean? Does this guy have symmetry? Yeah. So symmetry is if you look at like this, like look at these circles, don't look at the arrow. Look at these circles. There's symmetry, right? I could cut it this way and fold it in half and it matches. I could cut it this way and fold it down and it matches. So I'm going to pick a letter. Let's use the letter B. Okay. Pretend that these two bumps are the same size, okay? Because I can't draw very well. Does this letter B have symmetry? Everyone says yes or no? Yeah, it does. It has symmetry this way. Good. Okay. Does it have symmetry this way? No. Why doesn't it have symmetry? Because this side does not look like this side. Okay. If you look at your face, take a picture, look at your camera, look at your face. Your face has symmetry. Ms. Johnson's going to do a great job of drawing. Okay. So you have an eyeball on this side. See, look how good that eyeball is. I know you guys are like, Ms. Johnson, why are you a teacher? You should be an artist. You know, you have an eyeball on that side. You have half of a nose. I'm not even going to draw a nose because you guys would all laugh. You have half a nose on one side and half a nose on the other. You have half of your lips on one side and the other half on the other side. See, look how cute you are. I'm a good artist. Look at that. That looks exactly like you. Like, oh my God. No, I'm just kidding. Okay, so symmetry. Does this guy have symmetry? And you guys would all say yes or no. Yes or no? Yeah, because I could fold it, right? There's a couple different places I can fold it, which I think is interesting. I could fold it this way, right? Like if I take the line y equals x. Oops, apparently it likes y equals x, my bad. Y equals, if I correct, oh, it's off, that's why. Okay, if I take it and fold it along this line, do you see how it works? So yes, there's symmetry. Let me write that down. I need a different color, green. So yes, so it has symmetry over, that's not how you spell symmetry, you guys. I'm just testing you. Over the line y equals x, right? It has the symmetry over the line y equals x. Is that the only place that I can draw a line? Y equals x. Yeah, y equals x works. Yes, definitely. Is there another line that I could do? Yeah, someone said it. Y equals -x. Is that true, Ms. Johnson? I don't know. Let's try it. Y equals -x. Let me ignore the blue line for just a second. Could I fold it over that green line and come up with the same thing? And you guys would all say, And the way you would check is you can plug in a negative value here. Like if I plugged in 4, right? Wait, let me get this right. If I plug in 4, so this point here is going to be this point here. So if I plug in 4 here, I get out 1/4. So if I plug in 1/4, I would get out 4. And the answer is yes, right? So I'm going to write that here. So y equals -x. Does it make sense when I put like symmetry over this and this. You guys all see that? There's also one more symmetry, and this one's weird. It's not a folding, it's like a rotating. Could you imagine that I rotated this, like I took this and I spun it until this guy became this guy? Can you guys imagine that? Can you imagine me spinning this? So like an arrow, I need like an arrow. Give me a second. Let me draw like a little arrow. So I rotated it this way or the other way, it doesn't matter. But can you imagine that I rotated this part right here, maybe this point right here, until it got all the way to this point right here? So let me draw that better. So I'm going to pretend that I take this point, and I'll take this point because everybody knows this point is 1, 1. So big point right there. And then I rotate it until he gets to right here. Do you guys all see my rotation? It's a great circle, isn't it? Do you see how it has rotational symmetry? This might be a new word for you, so it's okay if it doesn't make sense. So I'm going to just write it. And then if it doesn't make sense to you, just like kind of like sit it in the back of your head and be familiar with it. So it also has rotational symmetry of 180 degrees around the origin. So whenever I talk about rotating something, I'm going to put this down here so it's you can see it. Whenever I talk about rotating something, I need two things. I need the degrees. How much are you going to turn? And around what is the center? So around the origin. You guys all see that? So pretend that this is like a merry-go-round and the center is at 0, 0. So this guy ends up right here. So this is a lot of imagining that I want you to think about. How else can I show you this? Ooh, I have a really weird way that I could show you this. Give me a second. Okay, so I really like this site. It's called Mathagon, and it kind of shows really fun things. This is a tangram. This is a parallelogram. And what I want to show you is what rotational symmetry looks like. Okay, so the first thing that I want to do, oops, I want the same guy. I want 2 of these. Okay, so I'm going to show you, make his color different. Blue. Okay, I'm going to show you that this has rotational symmetry by number 1, putting it on top of the other one so you can't see them. Okay, and I'm going to turn this guy until the guy disappears again. Do you see how that works? So this parallelogram has rotational symmetry of 180 degrees. And the center is, I'm just going to call it the center of the parallel. I'm not even going to tell you what it's really called. Okay. So if I rotate this 180 degrees in either direction, and you should know why I say either direction, it has rotational symmetry. Now this guy, does this guy have rotational symmetry? What do you think? Yes or no? Does this guy have rotational symmetry? My little triangle guy. The answer is no, right? Because I can't turn him in such a way that I can make that blue guy get completely behind my pink guy unless I go all the way around at 360. Now, it's not called rotational symmetry if you go all the way around, because you end up back to where you started, right? If I told you guys to do a 360, right? Although that is a really cool trick if you snowboard or skateboard, right? But if I told you to do a 360 when you're just sitting in your chair, all you did was you turned all the way around, right? So there's no rotational symmetry for these shapes. Okay, there is rotational symmetry for this guy because I didn't go 360 degrees and I had him disappear. All right, moving on. Okay, takeaway 2. So end behavior, we should consider as well. Let me clear my little screen here. You need to go a little faster, Ms. Johnson. All right, not a big deal. So here, 1 over x, end behavior. Yes, it has end behavior. What's happening at the ends? What's happening at the ends, guys? As x approaches, oops, need spaces. X approaches infinity, what's happening? F of x goes towards where? Yeah, it goes towards 0. Very good. And this is actually true for both ends, right? So I'm going to say as x approaches negative infinity, f of x also goes towards 0. How do you know that, Ms. Johnson? Because as I go all the way out, it's going towards 0. As I go all the way to the left, it's going towards 0. What are your asymptotes here? Your asymptotes. What are your asymptotes in this case? We talked a little bit about this. What can't it be? Yeah, it's zeros, right? Y equals 0 and x is equal to 0 are your asymptotes. So y equals 0, x equals 0. They have an asymptote at both. Your job is to be like, where does that show up here? And you're like, but ma'am, Ms. Johnson, there's a bunch of zeros. Yeah, that's your job for today's lesson, right? Your domain. Look at your domain. Look from left to right. Left to right. Is there any is there any number that it can't be? Yeah, it can't be 0. So negative infinity, comma 0, and these are parentheses, notice, and 0, comma infinity. Yeah, right. The range is actually the same thing. So let me copy this. Are you going to let me copy? The range is actually the same. If you go from bottom to top, right? You can't have a 0 again. The intervals of decrease, the whole thing is decreasing. So it decreases from negative infinity to 0 and from 0 to infinity. Ms. Johnson, you want me to do this again? Yes, do it again. So here I should say, can't, oops, I didn't want this in English, not in enough. So here we can't plug in 0. Here, 1 over x will never equal to 0, right? Here, the whole thing is going down. It decreases, boom, boom, right? From left to right, we're going down. From left to right, we're going down. But Ms. Johnson, you had to go up to get to that other branch, but that's not part of the function, right? That's the second branch. So your intercepts, did you have intercepts? No, they didn't touch. And it also says it right here. Your asymptotes are that. Did you have a maximum? No. Ms. Johnson, can't we put infinity? No, because it's not a real number. It's not a real point, right? And no, you can't put a minimum. So this is none. Any questions on this, guys? So always come back to here, because if I ask you for these things, I'm going to ask you for the domain of a function. It's not going to be a 1 over x. It might be like 1 over x plus 5. Hey, look what it did. Anyone want to describe what it did when I put plus 5? What did it do? What did it do? Yeah, the whole function moved up 5. Huh. I wonder, and this is what you should be asking. I wonder how that affects my end behavior. I wonder how that affects my asymptotes. I wonder how that affects my domain, my range, my intervals of increase, and my intercepts, right? So because it moved up 5, oh, that means all the y stuff is going to change to 5. I don't know. I'm just saying. I'm guessing. Yeah, it looks like there's an asymptote of 5. So that's going to be y equals to 5, huh, Ms. Johnson? Oh, but it's not going towards 0 anymore. It's going towards, hey, Ms. Johnson, it's going towards 5. Oh, is that true? I don't know. We're just guessing. All right, enough of that. Last page. When the equation is given in standard form, try to factor it to find its roots. When the equation is given in standard form, use technology to graph to see if those real roots can be verified. This is pretty good. So basically they're telling you, make sure you factor. Okay. All right, good job.